after a long time I'm actually you, and it is also great that you are remembering.
Yes.
I'm
Yes. Yes.
audible?
Yes, sir. Yes, sir. Now
Uh,
audible.
some problem with, okay. So should I share my slide first and then okay, thank you, Kushum, for
Yes.
a long introduction. I'm just a teacher like you also. So, and you have assigned me to, for a introduction to probability. And since it is a very tough to define even the probability, I don't know how I can take the class, but I will try to make whatever the understanding I have. So, okay. Slide is visible.
Yes, sir. It's visible.
It is a full screen. Okay. So,
Yes, now it's full screen. Yes.
my topic for this talk is Introduction to Probability. And since I already told that it is a really no answer to this question, what is a probability? But I'll try to make whatever the people think about the definition of probability, and we'll also make that whatever the probability theory are till date established by the researcher. So some people think that it is a limiting frequency, and that is to say that the probability of getting heads, like an example, when a coin is tossed, means that if the coin is tossed many times, it is likely to come down heads about half of the time. But if you toss a coin 1,000 times, you are not likely to get exactly 500 heads. So you would not be surprised to get only 495 or 510. But what about 450 or 100? If I can get 450 or if it is a 495 or 505, it is almost half of the time we are getting at. But say, suppose in 1,000 toss, we are getting only 450 time, then we cannot say that it is a half. Then it is a 0.45, or if it is 100 times only. So then it is not the exact definition that limiting frequency will be the probability. So let's take another, this is statement from the other people. There's some people, if we see the second bullet, there's some people would say that you can work out probability by physical argument, like the one who use for a fair coin, but this argument does not work in all cases. It does not explain what probability means. I'm taking one example of, like, if we say that probability is that how many options are there and what you are looking, just the, say, the tossing of coin, there is an option is that either head or tail. So probability of head will be, will be 1/2. So this is actually physical argument, but this physical argument fails. Like if I say a ceiling fan is hanging, so what is the probability that it will fall? So then it will either hang or it will fall on the ground, but it is not half. We know that this is it is a very rare chance that a ceiling fan will drop. Means it is, if I see thousands of ceiling fan. So it is, it may happen that 25 years, one ceiling fan can drop, but it is not half. So this argument, physical argument is also fails. So now I'm coming to another, some people say that it is a subjective. You say that the probability of head of in a coin toss is half because you have no reason for thinking either head or tails. More likely, you might change your view if you know that the owner of that coin is a magician or a fraud man. If it is a magician or fraud man, you may change that chances of it may not be in half because he may change, or his coin is a biased coin. So, but we cannot build a theory on something subjective. So now I'm coming to the definition, that actual definition of probability is given by all the probability theory. When this is Kolmogorov, a mathematician from Russia, he defined some axioms. On the basis of his axioms, now we can see that how we can define a probability. So you can see that this is what are those axioms, and all of we know from our school days that probability is a probability of an event, probability of event on a sample space. We can calculate just looking into in the how many points in our event space and how many points in the sample space. It is actually well defined by these axioms of A and Kolmogorov. So let's see that what are those axioms actually stated by the Kolmogorov. Kolmogorov has stated three axioms. First one, if A is an any event, A is an any event, then the probability of A must satisfy these three axioms. So first one, for any event A, we have the probability of A should be greater than or equal to 0. Equal to 0 means if the event never happened or it is an impossible event. Otherwise, its probability will be greater than 0. And that second axiom, that probability of the sample space, whole sample space, will be 1. Means if it is a certain that if we have taken that an event is a whole sample space, then event will be happen on the sample space only. So it is always a certain. So its probability is 1. It means that probability of any event A will lie between 0 and 1. Between 0 and 1. But most interesting is the third axiom. If the events A1, A2, means it may be that finite or infinite number of pairwise disjoint events are there, then this probability of A1 union, A2 union, all these events is equal to the sum of the probability of that each individual events. So on the basis of these three axioms, now we'll see that how we can define that probability of an event A is the number of this is points in that event space A divided by the number of points in the sample space. Now we'll see that how these three axioms can define us the probability, how we can calculate a probability of an event. So just looking into this at the bottom part, a proposition I have stated, this proposition, if we see this proposition, just I can mark her. Okay, this proposition, if we see the last part of this, okay, I can use cursor, proposition 1, and that if the event A contains only a finite number of outcomes, say A has a event has a A1, A2, AN, then the probability of A is the probability of A1, A2 up to AN. Since these points, finite number, these outcomes are disjoint outcomes. These are independent outcomes. So the probability of A will be sum of the probability of individual outcomes. So looking in the broader sense, we can, since if this A is our, suppose A is our the whole sample space, and sample space has A1 to AN outcomes. So then sum of the probability will be 1, because we know that probability of the sample space is 1. So the sum of this is PA1, PA2 up to PN will be 1. Now we see that if there are n outcomes and are equally likely, and their probability sum is 1, then each has probability is 1 by n, because they are if they are equally likely, then each of these probability are same. So I can say that probability of each of the are same because they are equally likely. Then each of these probability will be 1 by n. So that is 1 by the number of points in the sample space. Now going back to the proposition 1, if I now going back to the proposition 1, we see that if all the outcomes are equally likely, then probability of A will be number of points in the event space divided by the number of points in the sample space for any event A. Justifying the principle we used earlier, that probability, say in the case of now I can say using this this Kolmog's principle, that probability of the head in a tossing of coin is 1 by 2, because if I say this is tossing a single coin, so there is a chance either it will be head or tail. So sample space has a 2 points or 2 outcome, and our favorable outcome is head. So head is only 1, so 1 by 2. So with this principle, we can we'll take this probability of an event, we'll calculate by this formula, that probability of A is the number of points in the event space, favorable event space, divided by the sample space. Now, as we we know that probability, since we can have joint probability also, like if we have A and A, so here I'm any two events, say AB, then we know that probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. How it is? So if I take, say, A union B, I can have, so just I make, I'm trying to attempt. There is some problem with that pen. Okay. So this I can prove in orally itself. Say if I see that if I see the Venn diagram of A union B, there is a 3 disjoint. I can define by 3 disjoint set. Like A1 is the A minus B, means A event A minus B means the events which are outcomes which are in A but not in B. So that is A1, and I am defining A2 is A intersection B. A intersection B is A2. A intersection means the events which are common in A and B. And third group, say A3 is B minus A, means the outcome which are in B, not in A. So now, if I break down all this right-hand side, what will be PA? Here PA will be probability of A1 plus probability of A2. Why? Probability of A1. So what is A1? A1 is A minus B, that event A minus B. And what is A2? A2 is A intersection B. So probability of A, I can define probability of A1 plus probability A2. And what will be the probability of B? Probability of B will be, so probability of A2 plus probability of A3. Probability of A3. And what is probability of A intersection B? What is probability of A intersection B? A intersection B is our probability of A2. So if I substitute things, so we'll get probability of A union B. You can see that if I substitute this, we'll get probability of A1 plus A2 plus A3. And if I see directly, if I calculate probability of A union B, where A1, A2, and A3 are disjoint events. So probability of A1 union probability of A1 plus probability of A2 plus probability of A3. So from there, we can justify this formula. Having a 3 events, A, B, C. Then, and we are calculating the probability of A union B union C. In that case, I'm audible to you? Hello? Because there is an internet showing that unstable.
Yes, sir. Audible.
Okay. Okay. So probability of A1 union A union B union C means I'm looking for the probability of these 3. So since it is not mentioned these events are disjoint or not, so in that case we'll write most general inclusion exclusion principle. So we'll see that probability of A plus probability of B plus probability of C, and we are subtracting that common points between AB, AC, and BC, and we are adding common of all 3. So if we just the way we prove the first proposition, we can also prove the proposition by dividing the whole region A union B union C into multiple disjoint set events. So this can be generalized for any number of events. So this is in probability, we use, say there are multiple events are there. So, and we are looking for this union of these events. So we can use this formula or the generalized formula of that. So, and few more standard formulas we use in means in probability because these are probability when we are calculating probability between the events, we can always use by Venn diagram. And if we can make the this is disjoint, this is disjoint sets, and from there we can use the third principle of cosmograph. We can and we can establish all these the laws in probability, and we know that this is distributive law is in the set. We can also use the probability principle because in distributive you can see that that A intersection B union C this all so if I apply this first proposition, then this will be probability of A intersection B plus plus probability of C minus probability of A intersection B intersection C. And same thing, if I expand in the right hand side, also we'll see that it will probability of, so this probability of left hand side will be the probability of right hand side. Okay. So now I'm coming to another interesting point in the probability. If A and B are two independent events, then probability of A intersection B is probability of A into probability of B. Why so? So if we are, for an example, if we are looking for that two independent events, like from school level, we know that examples are always given in terms of tossing of coin or throwing of dice. So say tossing of coin and throwing of dice. So we are looking for two independent events that I have tossed a coin and I have thrown a die, die, and I'm looking for if head appears in the tossing of coin and odd numbers coming in the dice. So these two events are completely independent events. So I'm looking for that it should happen jointly, means I'm looking for head and odd number in the dice. So that will be, so what will the chance of head? We have already calculated the probability of head is half, because in tossing of coin, that probability of head is half. And this is in the throwing of die, the probability of coming odd faces is also half, because either it will be 1, 3, 5. These are the three odd faces, or the even faces are 2, 4, and 6. So there is a in the favorable, this is favorable. This event is 1, 3, 5, and over the sample space is 1, 2, 3, 4, 5, 6. So 3 by 6 is half. So half into half is 1/4. Means 1/4 chance that this is tossing of coin will appear head, and this is tossing of die simultaneously will also get this is odd faces. So this is for intersection, means two independent events. These two independent events we can generalize for n independent events also. Let A1, A2, An be are mutually independent events. Then this intersection of probability of intersection of A1, A2 up to An will be product of all these independent events. Another interesting, and that when we are calculating the probability, it may sometime it is required that what is the chance, because we have to calculate, say we are looking for this is if we see that in the bottom, I have stated one theorem, the number of selection of k objects, because now sometime we have to select k objects from n objects. Then we know that if it is a ordered sample, if the sample is ordered, say all the objects are ordered by 1, 2, 10. We are doing with replacement, then this is our selection will be n to the power k, because every time we have a n options. Every time we have a n options, and we have selected k because we are replacing. So there is a every time we have a n options, and we are selecting k times. So this is n raised to the power k, because every time this events will be an independent event from the previous one. So n raised to the power k, because of this product rule. And this is when with replacement, when it is without replacement, in that case, it will be changed, because in the case of without replacement, it will be NPK. What is NPK? It is actually, we know that the first attempt it will be there is a n object, so anyone from the n can in the first chance, and we have not replaced. So rest n minus, in the second attempt we have to go for n minus 2 objects. From the n minus 2 objects, 1 objects are selected, so it will be again we have a option of n minus 1. So n minus 1, and subsequently it will be n minus 2, n minus 3, and we have to go n minus k plus 1. So this is nothing but factorial n divided by factorial of n minus k. And factorial n divided by factorial n minus k is nothing but npk permutation. So npk. So this will be the these many ways we can select k objects from n object without replacement. Similarly, if if it is an unordered sample again without replacement case will be same, but in the case of with replacement, it will be NCK, because here this is objects are not ordered, so it will be this is number will be less than the case of ordered sample. Okay. Now I'm coming to another interesting point in the probability, that is called conditional probability, and which has a wide applications in our life, this conditional probability. So suppose that we are given that an event E has occurred, and we want to compute the probability that another event A occurred. Means E is already occurred, and we are looking for that another event A will occurs. In general, we can no longer count, and since the outcome may not be equally likely. The correct definition is as follows. I'm just defining at the bottom. Let E be an event with non-zero probability. That first event has a non-zero probability, means first event must, when that it should be, it is not an impossible event. And let A be an any event, then the conditional probability of A given E is defined by probability of A given E is defined by probability of A intersection E by probability of E. Or I can say that this is A, probability of A given E into probability of E is equal to probability of A intersection E. So this is actually our conditional, this probability, our conditional probability that A given E. So let's take a simple example on that. Say a random car is chosen among all those passes through a particular junction. Say here it is Trafalgar squared, some squared of US on a certain day. The probability that the car is yellow is 3/100, means only 3% car is yellow. And the probability that the driver is blondie means either he has a this is fair here, or it is a pale yellow here, means hair color is 1/5. And the probability that the car is yellow and the driver is 1/50, means driver, the hair color is white or pale yellow, so it is 1/50. Find the conditional probability that driver is blend A, and given that the car is a yellow, means it is given that now we have to calculate that what is the probability that driver is blend given that the car is yellow. So here probability car is yellow first, it should be car is yellow. Now we have to see the hair color of the driver. So if Y is the event that the car is yellow and B is the event that driver is blending, then we are given that the probability of Y is 0.03. It is a 3/100. It is 3/100, so 0.03. And probability of the probability of B means that driver is 0.2. 1/5. 0.2. It is 1/5. And the this probability that the car is yellow and driver is 1 by 50, so 0.02. So now we have to calculate the probability of B given Y. B given Y, because that driver is D and now car should be no. Car is yellow. Now driver should be hair color. It is must satisfy. This is either the pale yellow or white. So this we can calculate that this is B given Y. So probability of B intersection Y by probability of Y. So probability of B intersection Y is 0.02 and probability of Y is 0.03. So its chance is 0.667. It means that 2 out of 3 will be of that. 2 out of 3 will satisfy this. The probability is 2 out of 3. So note that we have not used all the information given. So you can see that we have not used all this information. The probability of B information are not used anywhere in this. So there is a connection between the conditional probability and the independence. Now I'll also define the conditional probability and the independence. If say B and Y are two independent events. B and Y are two independent events. What happened? Then probability of B given Y will be probability of B into probability of Y divided by probability of Y. So, and since probability of Y is non-zero, so we can cancel out. So we can get the probability of B given Y is probability of B. Or you can see the given proposition 2.1 that let A and B are be given with probability of B is not equal to 0, then A and B are independent if and only the conditional probability of A given B is equal to probability of A. Probability of A. So this must satisfy. Now I'm coming to next thing on the conditional probability, the Bayes' theorem. Bayes' theorem is it is widely used in many of the decision-making system, and nowadays in data science and the data mining, we use the Bayes' theorem very frequently for many, like in the Bayesian also, Bayesian classifier. It is based on this theory only. So what is the Bayes' theorem? So let A and B are two events with non-zero probability. If they have a non-zero probability, then the probability A given B will be probability of B given A into probability of A divided by probability of B. Or we can see the probability of A given B into probability of B. What is these two product, probability of A given B into probability of B will give this will be equal to probability of A intersection B. Again, if I go for probability of B given A into probability of A, this also leads to the probability of B intersection A. And since probability of A intersection B is equal to the probability of B intersection A, so this is established in straight way from our previous knowledge. So this formula actually are extended further also. So if probability of A is neither 0 or 1 and probability of B is non-zero, then we can also so if probability of A is neither 0 and 1, it means there will be an if the probability of A is say anything A, then probability of A complement will be 1 minus A, because A plus its complement complement, this sum of this probability will be 1. So in that way, there will be this is a negation of A, or the complement of A is exist. If A is an event, so negation of that event is also exist. So this is why I'm saying that probability of A is not equal to 0 or 1. So in that case, if I expand this this row, so numerator is same, Now denominator PB we can expand by adding up two. This is conditional probability. You can see that this is probability of B. I can write by this expression. What is that? That B given A into probability of A plus probability of B given A complement into probability of A complement. So this has a, now I'll also discuss one example why we are looking for this formula, because this formula, this is our, we know that from the, this is our conditional probability, it is 1 in a we can establish. This also we can, the probability of B is nothing but probability of B given A into probability of A, and probability of B given not A into probability of not A. Means whole B. B can be divided into 2, that either with A or with not A. So this is actually probability of B can be split into 2 parts. So now take a simple example. We can look into this simple example. Say consider the clinical test described at the start of this section, that suppose that 1 in 1,000 of the population is a carrier of the disease. Suppose also that the probability that the carrier test negative is 1%. While the probability that a non-carrier test positive is 5%. It means that now I'm taking events, there are 2 events. Say, let A be the event is the patient is carrier, and B is the event, the test is, this test result is positive. Test result is positive. So there are 2 events, A, the patient is a carrier, and B is the test result is positive. So it is given that the patient is a carrier is 1 by 1,000. So the probability of A is 0.001. So the probability of A complement will be 0.999. 0.999. So so probability of B given A, it is also the 0.99, because here it is given that that the probability that the carrier tested negative is 1%. So a positive will be 0.99, and probability of B given A complement is 5%, because here you can see that probability that a non-carrier tested positive. So a non-carrier tested positive, positive is 5%. So now all this information, if I put in this formula, that now I'm looking for 2 cases. That first case, that a patient has just had a positive test result, and what is the probability that the patient is a carrier? The answer is, so I'm looking for that it is given that patient is a positive, tested positive. So B is given that he is a tested positive. And what is the chances that the patient is a carrier? A is the patient is a carrier. So A given B. So A given B, if I use the last formula, this formula, if I this formula, so this will be probability of B given A into probability A divided by the denominator is probability of B. B can be split into two parts. That probability of B given A into probability of A plus probability of B given not A into probability of not A. So if I substitute all these values, we are getting this. It is almost 2%. So it is actually, I'm looking for this answer that a patient has just had a positive test result. And what is the probability that the patient is a carrier is a 2%. Now I'm coming to another question in this, another part. I'm looking for a patient has just had a negative test result. What is the probability that patient is a carrier? The answer is just I'm putting here that it is a test result is negative. Test result is negative, and he has that patient is a carrier. Means A is a patient is a carrier when test result is negative. So if I calculate by the same formula, we are getting very rare chance. The probability is very small. 0.000 after 401 is coming. So patient has a patient with a negative test result can be reassured, means almost reassured, because it's almost 10 out of 10,000, it is chances 1 by 10,000. So, but a patient with a positive test result still has a less than 2% chance of being a carrier. So it is likely to vary unnecessarily. So in this case also the patient with a positive, so it is also having only 2%. So it is unnecessarily vary. So this is actually this calculation. So this example was created during this corona and other pandemic. So of course this calculation assume that the patient has been selected at random from the population. If the patient has a family history of disease, the calculation would be quite different. It is, I'm taking that that there is no family history and others are not considered, then these values are okay. But if the patient has a family history or the disease is a hereditary disease or other, so this calculation may not work. Now, because in probability, so this is the basic of the probability. Probability. I told about that what is a probability and conditional probability, and that and conditional probability, the Bayes' law. These are the fundamentals in the probabilistic theory. Now, in probability, there is a most important part is the probability distribution. So I'll concentrate. There are two types of probability distribution. It may be discrete and it continuous. So if time permits, I'll go for continuous. Otherwise, I'll take only the discrete probability distribution. Discrete probability distribution will understand from the base that how the discrete probability distribution are generated. Because every distribution, first we have to know about the, because every distribution based on a random variable. So first we'll define what is a random variable for both discrete and continuous cases. Then we'll talk about different type of discrete probability distributions. So first, what is a random variable? A random variable is a numeric outcome that results from an experiment. For example, say suppose we have thrown two this is dice, and we are observing what faces are coming. And so our sample space, what is our sample space? Our sample space is if it is possible to write, okay. Don't know how it can use pointer. Okay, so in sample space, okay, I cannot right here. So sample space is actually S. If I write sample space is S, so S will be, S is actually our set of all, this is 1 less than or equal to I comma j, I comma j, I comma j less than or equal to 6. This is our sample space. Sample space has this, means I and J are the, say, faces. We are looking for the faces of the dice. That what, this is our sample space is actually has a all 36 points. 36 point. Now, I am looking for to create a random variable that the sum of the faces, sum of the two dice faces. So in that case, so what will be the range of the random variable? Hello, I'm audible to you. Hello.
Yes, sir.
So just a simple question that our samples, I have thrown two dice on here, and now the dice fall on the floor, and now we are observing what are the faces on the die. So our sample space will be I is the first, first dice faces is I, and the J is the second. So I and J both will lie between 1 to 6. So our sample space is 1 to 6 by 1 to 6. So it is actually, so total, this is, it may be 1 1 1 2 1 3 1 6, then 2 1 2 2 2 6. So there are 36 points in the sample space. I'm looking for a random variable, create a random variable, and the sum of the faces, faces appear in the two dice. So here random variable, it is a discrete random variable, and the random variable can takes the value 2, 3 up to 12, because both are 1 1, then 2, and both are 6 6, then it is 12, and the rest of the value will be in between. So 2, 3 up to 12. The random variable can takes the value between 2 to 12. So this is just a simple example. So for each event, each element of an experiment sample space, the random variable can takes on exactly one value. And discrete random variable, RV means this is RV is our random variable, and RV that can takes only a finite or countably infinite set of outcomes. Then we'll call it as a discrete. And continuous, a random variable that can take on any values among a continuum, means in an interval it can takes all the values, then we'll call it as a this is continuous random variable. But maybe it may be discard something I missed. So random variable are denoted by upper cases X, and individual outcome of the random variable is denoted by lowercase small x, and the rest of the this is distributions. When we'll talk about the discrete or continuous distribution, we'll use this notation. This is capital X for the random variable and small x for individual outcome of the random variable. Now, we'll understand further on this random variable. And random variable X represents a numerical value associated with each outcome of the probability distribution. As I already told one example of that. A random variable is discrete if it has a finite or countable number of possible outcomes that can be listed. For example, here you can see that this is 2, 4, 6, 8. Say X can take these values, then it is a discrete. But in the case of continuous, the random variable is continuous if it has a uncountable numbers of possible outcomes, or it takes all the outcomes in an interval, then we'll call it as a continuous random variable. For example, here it can take values from all the values from 0 to 10. Okay. So I'm taking some example that decide if the random variable X is a discrete or continuous. First example, that the distance your car travels on a tank of gas. So a distance your car can travel in a continuous random variable because it is a measurement that cannot be counted. It may be I can reach up to 17.5 kilometer, you can reach 17.51 kilometer, and so on. So it is an uncountable. This one tank, we have not given the measure of tank of the car, and we have not given how much cc that car means engine was. So it will be limitless way we can. So we can use this as a continuous random variable. The number of students in a statistics class, it is a discrete because it is a countable. The number of students in a is a discrete random variable because it can be counted. Now, discrete probability distribution. So I'm coming to this discrete probability distribution. Discrete probability distribution listed each possible values of random variable can be assumed together with its probability. And the probability distribution must satisfy the following condition, that every discrete probability distribution must satisfy the following condition. The first one, that the probability of each values of the discrete random variable is between 0 and 1, because each point the probability between 0 and 1, and sum of the probability at all this point will be 1. So a probability distribution and discrete probability distribution. So this is summation. In the case of continuous distribution, it will be integration. So in the case of discrete probability distribution, that probability of each point of the random variable will lie between 0 and 1, and the sum of the probability of all the points in the random variable will be 1. So how we'll construct a discrete probability distribution? We'll see that step by step how we can construct a discrete probability distribution. So let X be a discrete random variable with possible outcome of that variable, that here this X will be capital X. This capital X, let a discrete random variable with outcome small x, x1, x2, xn, and make a frequency distribution of possible outcome. So first we'll see that frequency distribution of all possible outcome. Find the sum of the frequency. Then find the probability of each possible outcome by dividing its frequency by the sum of the frequency. Check that each probability is lying between 0 and 1 and sum is 1. So let's take one example. Okay. So let's take one example. Say the spinner below is divided into 2 sections. The probability of landing on one is 0.25 because you can see that 1/4 of the circle is blue color and 3/4 is purple color. So, and blue is 1 and purple is 2. So the probability of landing on 1 is 0.25 and the probability of landing on 2 is 0.75. Let X be the number of spinner lands on, means where it will land. So construct a probability distribution for the random variable capital X. These are capital X. Capital X. Okay. So we can see how we can construct. Here already in that, if I take the random variable X can take two values, 1 and 2, its probability is 0.25 and 0.75. It satisfies both the condition that probability of each point on the random variable is between 0 and 1 and sum is 1. So now I'm going further. That the spinner below is spun 2 times. The probability of landing 1 is 0.25 and the probability of landing on 2 is 0.75. Let X be the sum of the 2 spin, means our random variable is the sum of the 2 spin. Construct a probability distribution for the random variable X. So what will be the value this random variable can take? Because we are spanning 2 times and either it can stop at 1 or it can stop at 2. So it can stop, that arrow can stop either 1 or 2. So what are the options are there? So, and we are looking for the random variable be the sum of the 2 spin. Sum of the 2 spin, it may both the spin it stop at 1, then 1 plus 1, 2. And this is one time it stop at 1 and another time is 2. So 1 plus 2, 3. And it may happen that both the time it stop at 2. So it is 2 plus 2, 4. So here random variable can take 3 values, 2, 3, 4. So the possible sums are 2, 3, 4. So now that sum of 2, when it occurs, that in each spin it stop at 1. And since spinning of this spinner is independent, that each spin is independent, so the sum 2 means both 1 plus 1 will come, that probability of 1 into probability of 1. So probability of 1 is 0.25 into probability of is 0.25. So it is 0.25 into 0.25 is 0.0625. Now I'm coming for, so we have calculated that sum of spin X2, it is this is probability is 0.625. Now I'll calculate the sum 3. Sum 3 when it will come. Sum 3 when the first either first spin or the second spin, it is say it may come in 2 ways. One is first spin is 1 and second spin is 2. So in that case, we have a joint, this is, so the independent, both the spin are independent. So the probability will be 0.1875. Or it may happen the first spin is 2. This first spin, it stops at 2. And the second spin on 1, then it is 0.75 into 0.25. Again, it is value is 0.1875. So both the options may come. So it may either of this. So the probability of 3 will be sum of this and this. So here probability will be 0.375. So probability will be 375. Sum 3, the sum of these two will give you this probability of the random variable 3 will be random variable 3 will be 0.32.
Your bill.
Okay. And now if I go for sum 4, there is only one option. Both spin, it will stop at 2. So here probability will be 0.75 into 0.75 is 0.5625. So you can see that all this probability lies between 0 and 1. And if I add all this probability, it will be 1. So it is a discrete probability distributions. These are the examples that how we can construct a probability distributions. So now, graphically also we can see that how this probability distribution for 2, it is 0.06, for 3 it is 0.375, and the point at 4 it is, so this is our pattern of this probability distribution. It is increasing. Mean of a probability distribution, the mean of a probability distribution, the mean of a discrete random variable is given by that mu is summation of x, that random variable, the value of the random variable, and the probability at each point of the, means product of point each, this is each point of the random variable into the probability at that random variable. This sum will give you the mean. So now we'll understand that each value of x is multiplied by its corresponding probability, and the products are added. So just see, in this case, the last case, what will be the mean of this probability distribution? Mean of this random variable, mean of the random variable. So if I multiply 2 into this, so this will come. So mean, we can see mean will be 3.5. So mean of this last probability distribution here, random variable is 2, 3, and 4, and its mean is 3.5. Mean is in between these two. Variance also, we can calculate variance also. Variance is nothing but that difference from the mean square of each of these points of the random variable into the probability at that point of the random variable. So if I calculate in the last example, so variance will come at 0.376. So variance is 0.376. So now I'll go for, so if we have a, this is random variable, this our variance is known, and now we can go for under root of the variance, it will give you the standard deviation. So this expected value or the mean value, just we have calculated. So just I'm going for another example quickly, that say in a lottery or the raffle, that 500 tickets are sold for $1, each for two prizes of $100 and the $50. What is the expected value of your gain? So your gain for the prize 100 will be the 100 minus $1 means $99. So this is, and the second gain is 49. So write the probability distribution for the possible gain of outcomes. So here our probability random variable is our gain. So 99 and 49. So 99, what is the or I can have loser also, because I have paid $1. It may, I am not winner of any one of these prizes. So there will be three possibilities. Either I will gain by $99, or I will gain by $49, or I will be loser by $1. So what is the chance of winning $99? Means gaining $99 is 1 by 500, because 500 tickets are sold. And similarly, in the case of gaining $49, it is 1 by 500. And losing this is $1 is because there are out of 500 tickets, two two prizes are there, so we can subtract that two tickets. Two will winner. Two tickets will win. One will be 100 and another will be 50. So probability of losing $1 will be 498 by 500. So these are also satisfy this all the probability of this each of these points of the random variable. Each of the points of random variable is between 0 and 1, and sum is 1. So this is this satisfy the condition of the random variable. Now our aim is to find the expected value or the mean gain of this raffle. So now if I calculate mean gain, so you can see that mean gain will be minus $0.7 because the expected value is negative. You can expect to lose $0.7 for each ticket you buy. So now I'm coming to some standard, this is discrete distributions. So first one is binomial distribution. I think all of you know about the binomial distribution. Quickly, I'll go through few of the standard discrete distribution. A binomial experiment is a probability experiment that satisfy the following condition. First one, the experiment is repeated for a fixed number of trials, where each trial is independent of other trial. There are only two possibility outcome of interest for each trial, that the outcome can be classified as a success or failure. Third, that probability of a success PS is the same for each trial. We'll take the probability of success of each trial will be same. So probability of failure of each trial will be remain same. The random variable X, here random variable X counts the number of successful trial. So here our random variable is a count the successful trials. Say now here, since it is a fixed number of trials, so if we can fix our number of trial is n, so what will take the random variable? Random variable X can take value 0 success. It may happen that all n trials the failure comes. So 0 success, 1 success, 2 success, up to n success. So we can descriptions we can give symbolically. The symbol n is the number of times a trial is repeated. P is the probability of success in a single trial. Q is the probability of failure in a single trial, and Q and P are related because either it will be the success or failure. So Q will be 1 minus P. So, and X is the random variable. You can see here random variable. The random variable represents a count of number of success in n trials. So the success may, 0 number of success may come, 1, 2, 3 up to n number of success. So now this is random variable can take, this is either 0 to success. So now I'm just taking one example on that binomial distribution. I have given the formula. Okay. So this is binomial experiment. How you can do that, decide whether the experiment is a binomial experiment or not. If it is satisfy the values n, p, q and the list of possible values of random variable x. If it is not a binomial experiment, explain why. I'm just taking one example. You randomly select a card from a deck of cards and note if the card is an S. If then put the card back and repeat this process 8 times. This is a binomial experiment. Why? Each of the 8 selection represents an independent trial because the card is replaced before next one is drawn. There are only 2 possibility of outcome. Either the card is a S or not. So it is you know that there are 8 trials. So probability of getting success is 4 by 52 because there are 4 cards of S in the pack of 52 cards. So P is 1 by 13 and Q will be 12 by 13. And our the random variable can take value 0 to 8. Means we have done 8-time experiment. It may be the never we got success, or it may success 1 time, 2 time, 3 time, or 8 times. Now we can see that another example. You roll a die of 10 times and note the number of die lands on. This is not a binomial experiment. While each trial roll is independent, there are more than 2 possible outcomes. 2 possible outcome, 1, 2, 3, 4, 5, 6. Because here, you know that in binomial distribution, outcome, either it will be success or failure. So landing a number in the die is may have 6 different options. So it is not that only success and failure, means it is not 2 outcome, it is a more than 2 outcome. So this is why this is not a binomial distribution. So now I'm defining what is a binomial distribution, the probability density function for the binomial distribution. So this is in a the binomial experiment, the probability of exactly X number of success in n trials is given by this formula. Sorry. Okay, overlapping is there. So this is the formula that out of n trials, X trials are successful trial. And so in this X number of success, the X number of success, we are in, so each time the probability of success is P, so P raised to the power X. And rest of the n minus X time, we got failure. So our probability density function, or this is our probability Px will be, we can define by this factorial n, because NCX factorial n by factorial n minus x factorial into x factorial, P raised to the power X and Q raised to the power n minus X. Now I'm taking one example on that. Say a bag contains 10 chips. 3 of the chips are red color, chips packet are red color, 5 chips are white, and 2 are blue. 3 chips packets are selected with replacement. Find the probability that you have selected 1 red chips. So a bag contains 10 chips packet, and 3 are red, 5 are white, and 2 are blue. And 3 chips packets are selected with replacement, and find the probability that you selected exactly 1 red chip. Means we have success here. Success is getting red chip is a success, and rest of the color is failure. So probability of success, you can see out of the 10 bags of chips, so only 3 are red colored. So our probability of success is 3 by 10, and rest are failure. Either it is a white or blue, it is a failure. So probability of failure is 0.7. Now it is given that there are 3 trials are made. We have and find the probability that you selected exactly 1 red chip. Means our success is one success in 3 trials. So X is 1 or such. So now if I calculate P at 1, so this will be 3C1, 0.3 to the power 1 and 0.7 to the power 2. So this probability of getting that out of this 3 tile, 1 red will be 0.447. Now I'm changing this problem slightly. A bag contains 10 chips. 3 of the chips are red and 5 of the chips are white and 2 are blue. 4 chips are selected with replacement. Create a probability distribution for the number of red chips selected. So since we have done 4 times, this is 4 chips are selected with replacement, means we have done 4 trials. So create a probability distribution of the red chip selected. So what will be our random variable can take value? Random means out of these 4 selection, it may be the 0 red chips are selected, or 1, 2, 3, or 4. So here in random variable as a 5 point, 0, 1, 2, 3, 4. So we can see already probability of P is 0.3, probability of success is 0.3, probability of failure is 0.7, number of trial is 4, and random variable can take 5 values, 0, 1, 2, 3, 4. So now we can see that its probability distribution we can calculate. Or we can calculate the probability distribution from the formula, the binomial distribution formula, that P0 will be 4C0, P raised to the power 0 and Q raised to the power 4. And similarly, we can calculate because this is the formula for binomial distribution. Yeah. Sorry. This is the formula for binomial distribution. So I can change the X 0, 1, 2, 3, 4. We can get the value of this probability. We can get the probability of each of these point the random variable. So this is the we can see that this is 1 no red, it is almost 24%. And 1 red, it is 41%. 2 red is 0.26%, 26.5%. 3 red color is only 7.6%, and 4 is very rare. So we already this. So now the following probability distribution represents the probability of selecting 0, 1, 2, 3, 4 red chips when 4 chips are selected. Find the probability of selecting not more than 3 red chips. Not more than 3 red chips. It means that we have to calculate the probability that X should be less than or equal to 3. So 0, 1, 2, 3. So if I add all this, so it is probability is almost 99.993%. Find the probability that selecting at least 1 red, So it will be the probability will be at least 1 red will be Px greater than or equal to 1. So it is 1 minus probability of 0. So 1 minus probability of 0 at probability at 0 is 0.24. So subtract it is 7.76. So this is the graphical representation of this experimentation. So, and the mean variance and the standard deviation of this binomial distribution. Mean of this binomial distribution we can calculate by mu is equal to NP. Standard deviation variance is NPQ, and the standard deviation is under root of NPQ. So just I'm not calculating this. I'm quickly few more interesting distributions which are actually different from the binomial distribution. I will quickly go through this next 5 minutes and I'll stop. So a geometric distribution is a discrete probabilistic distribution with a random variable x that satisfy the following condition. We'll see that there will be different from the our binomial distribution. A trial is repeated until a success occurs. This is different from the animal. Here in geometric distribution, a trial is repeated until a success occurs. Means at the first success, we'll stop the trial. The repeated trials are independent of each other, which is same thing as in the binomial distribution. The probability of success P is constant for each trial. This is also same with the binomial distribution. Binomial distribution. So here, the probability that the first success will occur on trial X is. So first, what will be our random variable? Random variable. I'm looking for the random variable X that satisfy the following condition. That first success. So I'm looking for only one success and rest are failure. So say if there are X trials we have made. So here out of X trial, one trial is successful. So till this success comes, each X minus one trial is failure. So we are done first trial failure, second trial failure, up to X minus one trial failure, and on X trial success occurs. So the PX probability of X we can define by that P into Q raised to the power X minus 1. So this has a many application of geometric distribution. I'm coming to another distribution. I think I have another distribution in this slide. Geometric distribution is actually the first success. There is a negative Poisson distribution. The Poisson distribution is a discrete probability distribution of a random variable X that satisfies the following condition. The experiment consists of counting the number of times an event X occurs in a given interval. The interval can be an interval of time, area, or volume. In the Poisson distributions, it may be anything. The probability of event occurring in the same of each interval. The number of occurrence in one interval is independent of the number of occurrence in other interval. The probability of exactly X occurrence in an interval we can calculate in Poisson distribution. The probability of X, exactly X occurrence or the X success means occurrence means success. X is it mu raised to the power X and e raised to the power minus mu divided by factorial X. So this is actually Poisson distribution. Poisson distributions, the probability density function is this, where e is exponential and mu is the mean of the occurrence. And probability distribution, mean of the distribution is mu only. Okay, I'll share this slide to participants so you can also see some of the examples actually in this slide. So because the time is limited, so I cannot, because probability distribution and the probability, it is not in one. I know that all of you are, so just I'm quickly recap the probability, basic probability definition and the few this is distributions, but probability, it is not in 1.5 hour I can discuss everything. So I will stop here only. So the probability distributions, in the probability distribution, we actually learned this, that how we can probability distribution, we can have described by table, graph, or the formula that describe the value of a random variable can takes on and its corresponding probability. Discrete probability distribution assign the probability to the individual outcomes. Continuous probability distribution I have not discussed, but assign the density at this is individual points, and probability of the range can be obtained by integrating the density function. Discrete probability density, discrete probabilities denoted by this sign, that probability of at a point, and continuous density function is Fy. It is, we cannot, since it is through integration, we cannot calculate at a point. So it is a cumulative density functions we can calculate by that up to y, that either continuous or discrete. In the case of continuous, it will be through integration, and in the case of discrete, it will be through summations. So I'll stop here with this slide, that probability y mass function we can define by this in the discrete case, and the cumulative distribution functions we can define, and in the case of discrete case we can define by this. So thank you. I'll stop here, and if you have any question on this basic probability and probability distribution function. Visham, I'm
Yes.
on time.
Yes, sir. Yes.
Because I think you have another lecture today, or one lecture.
No,
one day.
this was the last for today.
Okay.
Yes, so thank you so much, sir. Sir, we are having few questions, so can we take this?
Huh?
We are having some question. One question is there. Two questions.
Yeah.
So the first question is, what if conditional probability is 0 in some other scenario?
Conditional probability 0.
Yes.
Conditional probability may come 0 also, because if conditional probability, one condition is that the event which is already happened, means A after B, so B is already happened. So B probability should be non-zero, but probability of A and B is already occurred. It may be never happen. It may comes in this case also. So conditional probability may be 0 also. Means it is A is impossible when B is already occurred. So then probability, conditional probability will be 0. Your microphone is off.
Yes. So how much effective Bayes theorem as compared to conditional probability?
Actually, Bayes theorem is built on the conditional probability. Actually, this is the Bayes theorem. Base of the Bayes theorem is the conditional probability. All the this is Bayes theorem establishment, or the this is on the conditional probability. So this is Bayes theorem is a generalization, or for users point of view, this is more useful than the direct conditional probability, because it is actually sometime it is say A after B, it is not easily possible to calculate that A already happened and what will be the probability of B. Means I'm looking for A conditional, B conditional A. It is not easily possible to calculate directly, but from the Bayes law, we can translate this A conditional B to B conditional A. So if it is B conditional A is easier to calculate, so we calculate other conditional probability, and we can get the conditional probability of the in the A conditional B, we can calculate through the condition B conditional A. So this is why Beer's law is useful, that when it is a direct conditional probability is not possible. So we can go using the Beer's law, we can calculate in the reverse through the reverse conditional probability.